So let's see how powerful the Laplace transform technique when it comes to solving a differential equation. So let's look at a problem first. So let's say we have y double prime plus y prime minus 2y equals to 3 e to the t with the initial conditions y0 equals 0 and y prime 0 equal 1. So we have two initial conditions because it's a second order equation. So the first thing we notice is you can see that this is a non-homogeneous equation. So we have this e to the 3t term which is not equal to 0. It's a non-homogeneous. So when you have a non-homogeneous equation, what we normally do, we use the undetermined coefficient method. So if you are not familiar with the undetermined coefficient method, you can find a link in the description so you can learn about that. So we normally use the undetermined coefficient method when you have a non-homogeneous equation. And also to make things worse, and you can see that there are initial conditions given. So if there are no initial conditions, sometimes undetermined coefficient give you the answer quickly. But when you have initial conditions, it's going to be really long because you can see that you can only use initial condition at the last step when you want to find those unknown coefficients. Because we have like C1, C2 in this case. When you want to find C1, C2, you have to use initial conditions. So that means it should be at the last step. So that means you have to do all the algebra before we do that. And even if you make a single mistake and everything will be, you don't get the answer. So what we do instead, let's see how quickly you can get the answer using the Laplace transform technique. So that's the whole point of this one. So let's see how things gonna happen. So we have. So the first things first. So what we normally do when you get a problem like that, what we do, we first take the Laplace transform of the differential equations. That's the first step. So let's do that. So taking the Laplace from the equation, we have first is a y double prime. It's a second derivative. So that means it's going to start with s squared. So we have s squared ys is the Laplace transform of the solution minus sy0 minus y prime 0. So that's the first term. The second term going to give you is a y prime, is the first derivative. So that means going to give you s ys minus y0. That's the second term. And the third term going to give you actually it's a minus sign. There's a minus 2. So it's a minus 2 same ys. So you can see the same ys appear in all three places. The exact same thing. And then all the other ones are lowercase. That's the original function. Okay, and then on the other side you can see it is 3 is a constant, and then e to the t. We know that when you have an e to the t function, it is simply 1 over s minus a. That's what will happen. So in this case, a equal 1. That's the coefficient of t. So that means it's going to give you 3 over s minus 1. That's what you get. So the next step is to use the initial conditions. So we can use the initial conditions to simplify this a little bit. So let's plug in those values. So when you do that, first we can actually isolate the ys term. So you can write it this one as y s squared minus, in this case, plus s minus 2. So those are the coefficient of ys. So times ys. And then you can actually plug in the y0 term. So we're going to plug in the y0. There are two places, so you're going to plug in that. So if y0 is 0, that means you get a 0 for the first one. And then also y prime is 1. So when you plug in for y prime 0, you get a 1. That's what you get from the first one. And from the second one, there's a minus y0, which is 0. And then, so that's what you get on this side. And on the other side, you still have 3 over s minus 1. So the next step is going to isolate the ys term. So when you want to isolate the ys term, so you get s squared plus 2 plus s squared plus s minus 2 times ys. So if you bring 1 to the other side, you get 1 plus 3 over s minus 1. So that's what you get. Now the question is, there's like a mistake that some of the students do. they're gonna leave it like this one. So we are not gonna leave it like that, because that's actually depend on what you have on the other side. And you can see you have this expression which can be factored into s plus 2 and s minus 1. Those are two factors. And so what we normally do in this case is actually, because if you leave it like this, then you get two fractions. You get two fractions, and you can see that you cannot really find them directly. Even the first one, it is 1 over s plus 2 s minus, so we don't know exactly what is that. So in this case, what we do is we simplify this one. So this step is very important here, because we don't do that always. Sometimes we don't do that, because sometimes you can actually get this answer really quickly. But in this time, we actually going to simplify this one. So let's simplify this one, taking the common denominator. So you can write this one as s minus 1 plus 3 divided by s minus 1. And you can see this simplifies to s plus 2 over s minus 1. This actually turned out to be really good. Let's see what happens in the next line. So if you isolate for ys, you can see we have 1 over, so we're going to divide by fraction version now. So it is s plus 2 over s minus 1. That's the fractions. And then you can see on the other one, you have s plus 2 over s minus 1. So what happened? You can see this term get cancelled out. So it simplifies much better. And then you can see what you simply get is 1 over s minus 1 squared. That's what you get. That's the only thing you get. Now, after you get to this level, what you can do? So you know that you can actually use the partial fractions normally to write this one. But we also have a very nice shortcut, this one. So you can do the partial fraction method. And again, if you're not familiar with the partial fraction methods, because there are special partial fractions that we use for Laplace transform techniques that we normally don't discuss in Calc 2. So you can learn about that under a special partial fraction method video, and you can also find a link in the description for that. Now what we do actually, you can see that you can actually simply invert this one directly, because you can see the major form of this one is 1 over s squared. That's the major form. S minus 1 is the shifting part. So we can use the first shifting property for that. So if you want to learn more about that, then you can again find a link in the description about the first shifting property, how to use that. So the major form is 1 over s squared. So by the first shifting property, you can directly write the answer. So taking the inverse now, so you can see taking inverse, you can directly write the answer now. So it is simply yt, that's the inverse of ys. So it's the inverse of ys. So we take the inverse of the expression, and you can see the main form is 1 over s squared. That means it's a t. We know that the t is 1 over s squared. 1 over s squared is coming from t. The Laplace transform of t is 1 over s squared. And also, if you are not familiar with those ones, and you can also find the common Laplace transform table in the description. That's something like you need to remember, because it's going to make it things easy. And then that's the main form, and you can see there's a s minus 1. That means there's a e to the t term coming from the first shifting property, and you can see that's the answer. So in simple few steps, you can actually find the answer for this problem. So that is like a really amazing power of the Laplace transform technique. There are no much algebra here. There are nice simplification going on. But you can only see this one if you simplify. If you do not simplify to this expression, you can see you do not see that. So that means what will happen, this is like one of the major mistakes students do. They leave this as a like a different two different fractions, and then try to write this as two separate ones. That's like a big mistake, because then this doesn't happen. So then you even like in the second term, you see there's a repeated factor. So it's going to be really long, and you might need extra 10 minutes if you really do go along that direction, because you get two different fractions, so many terms. But here you simplify really nicely and get the answer really quickly without any major things. So now, just to compare, so let's see how we use this problem regularly, like in the other techniques. So use the undetermined coefficient method and see how we get this answer using the technique, just to compare the two. So let's do that now. So using the undetermined coefficient method, but you know that when you want to use the undetermined coefficient method, that's like another very powerful technique that when you want to solve non-homogeneous equations. If you have a term on this side, we have to use this, like one of the major technique other than variation of parameters. So there are other techniques, but non-homogeneous undetermined coefficient method is the most common one. So the first step is, if you have something like that, we try to write the solution of the homogeneous part. That's the first step. So for that, we can look at the characteristic equation. So if you look at the characteristic equation, so that's coming from the derivative part. So we write the characteristic equation, which is going to give you lambda squared plus lambda minus 2. So we set this one equal to 0. And you can see that this is like easy to factor. So the factors are lambda plus 2 and lambda minus 1. So that means this is going to give you two zeros. So the zeros are lambda equal -2 from the first one, lambda equal 1 from the second one. So that means we can write the solution now. So what we normally call the complementary solution, that's the first step to do. So it's a YC, which is going to give you a C1 e to the t plus C2 e to the negative t. So this is like how you normally solve constant coefficient differential equations. And again, if you need to know more about that, and there's a link in the description about how to use the constant coefficient differential equations. Okay, so that's the first step. So we're done with that. And then after we do that, then only we write the what they call a particular solution. So we're going to assume the particular solution. So assume the YP. Now there's an issue here. You can see this is like a normally like a e term, like 3e to the t. So when you have something like that, we normally write a e to the t. But you can see, unfortunately, that doesn't work here. The problem is, you can see e to the t is still already appear. So you can repeat it. So when you want to repeat, what do you want to do? You want to find a linearly independent term. Just to get a linearly independent term, what we do, we're going to multiply this one by the independent variable. Independent variable is t in this case. That means your guessing term, the yp, has to be some constant times t e to the t. So that means even in this step it makes it difficult because it's not like a regular e to the t term. So you can see that's getting like much more difficult. Okay, now what we do, the next step is we're going to find the derivatives. So what are the derivatives of the, and then you have to use the product rule. So you can see it's getting harder and harder. So let's try to use the product rule. So if you use the product rule, we derive the first term, which is a e to the t plus, and then we take the derivative of the second term, which is a t e t. So you can leave it like that, or you can even factor it. You can see aet is common, so you can pull it out. We t plus 1, so that you get. And then again, let's try to, because that's going to make it easy to take the derivative. So let's try to find the second derivative. That too, with second derivative, again, the first term is this one, going to give you a e to the t, so it is a e t. And then the second term times, so the t plus 1 derivative is actually 1, so we don't write it. And then the next what we do is we write the we take the derivative of the aet, which is aet again, times the second term t plus 1. So you can simplify this one also. So you can see that this is going to give you aet and then t plus 2. That's what you get for the second term. Now what we do, the next step is normally we substitute this to the differential equation. So let's do that. So when you substitute, the first term going to give you aet t plus 2, that's the first term, plus the second term going to give you aet t plus 1, and then you have minus, in this case 2y, so 2y means a t e t, equal on the other side 3 et, that's what you get. So what we normally do, we simplify this left side. So you can see when you simplify left side, actually this term going to cancel out with the AETT and the AETT. So those two terms get cancelled out. So that part is gone. And then just collect the rest of the terms. So when you collect the rest of the terms, you get 3. So you get 3 A E T. Then there's no T term. That's good because our choice was correct. And then you have on the other side 3 ET. So 3 ET. And this tells you that A equal 1 because you just compare the coefficients. You compare the coefficients of the linearly independent terms. That's how we do. So this is that. So equating coefficients. So equating coefficients. It's like a actual technique. So this is 3a equal 3. This is that a equal 1. You can see we are still not even getting the solution. Okay, so this is the a equal 1. So that means your yp equal t e to the t because a equal 1. Okay, so now what we write the general solution. So the general solution is, so you can write the general solution. These are all the steps that you need to do when you want to solve a problem using the undetermined coefficient method. So it is normally y equal, it is yc complementary solution plus the particular solution. That's what the theory says. So let's plug in here. That means it is c1 e to the t plus c2 e to the negative 2t plus the yp, which is tet. See, we are not done yet. So that is the solution. That's a general solution. So if you are given, if you are not given initial conditions, we done here. We just stop in this step. If you are not given initial conditions, but here, just to make things worse, you are given initial conditions. That means you have to find C1, C2 also. But you can see that there's a derivative term, so we take the derivative of this one. So let's try to find the derivative. So the y prime is what you get from the first term. It is C1 ET. From the second term, it is, you can see negative 2 c2 e to the negative 2t. And from the product rule, you get e to the t time plus tet by the product rule. So the product rule is, it is u prime v plus v prime u. That's the version we use because that's much easier to remember. Take the derivative of the first term like that. Okay. Now we use the initial conditions. Okay, so let's use the initial conditions now. So using initial conditions, so we have y0 equals 0. So that's going to give you, we're going to plug into the y expression. So you're going to get so what we had, so we have yt equals c1 et plus c2 e negative 2t plus tet. So let's plug in. So if you plug in 0, you can see you get c1 plus c2, you get a 0 here, and equal on the other side is a 0. So you get that equation. So the first equation is c1 plus c2 equals 0. And then we use the derivative one. So y prime 0 equal 1. So let's use that. See, we still don't know what's going to happen. Okay. And so that is a derivative one, which is this. So let's plug in 0 for this one. So that means this is going to give you c1 minus 2c2 from the first two terms. And then tet gets 0, but first one going to give you 1. So it's equal 1. On the other side, we have a 1 again. So that means this simplifies really well because you can see these two get cancelled out. But see, in this method, we don't know this until at the last minute. This is what is going to happen. So that's the problem with this technique. And then you get c1 minus 2c2 equals 0. So what equations we have? We have these two. And then these are not actually difficult to solve. So if you subtract these two, you can see that you get 3c2 equals 0. This is going to give you c2 equals 0. And if you plug into the first equation, you can see that you're going to get c1 equals 0. So c1 and c2 are 0. But the problem is you really don't know until at the last minute that they are 0. So that is the issue here. But with the Laplace transform, it's actually automatically happen in the algebra step. Remember, like you simplify those two fractions, 1 plus 3 over s minus 1. In that step, it's actually this part was done, the algebra part. But here we really don't know that until at the last minute. So that is the problem here. Okay, now C1 and C2 are 0, so that means your solution is simply, so you can say the solution is simply y equal by p. That's what happened. So that means it is simply t e to the t. So that is how we can use the Laplace transform technique to solve a problem. And I mean, this is how we use the undetermined coefficient method to solve a problem, but you can see it's really long. You get the solution only at the last step. So that is the problem with this. But sometimes, you know, this works for other problems. So that's why, so you can see how quickly you can get the solution using the Laplace transform technique. Is really amazing. Okay, now you can try these 2 problems or 3 problems just to see how things gonna go. So let's try these. You can try these as exercise. So we have y double prime plus 9y equal 5 half sine t, y0 equals 0, y prime 0 equals 0. And you can see when you have sine terms, things are even, sine cosine, things are even worse because you have to add 2 terms. So it's gonna get complicated and take derivatives. So you can see, and you can compare how fast you can get the answer using Laplace transform technique. So let's look at these and B. So next one we have y double prime minus y equal t plus 1 and y0 equal 0, y prime. So both initial conditions are 0. Okay, but still we really don't know until the last minute whether what's going to happen. Yeah, and you can see it's a non-homogeneous equation. And then let's try to see if you switch one of those conditions for the last one. So you can see in the last question it's the same thing here, but we have non-zero initial conditions. Okay, so let's try to solve this one using both techniques and see which one going to give you the answer quickly. And here you need to know like some algebra tricks, and you can find this answer in another video actually. Okay, so this is how you can use the technique. And please feel free to discuss this question in the comment section and how things gonna go, and you know what is your preferred method and things like that. Okay, so I hope this helps you. Thank you so much for watching.